start. Okay. Actually, this is the last page that I'm writing, but still, I'm recording that. And because so this one is a slightly more complicated model because it is a combination of both collision and friction. We know that once a block is hitting on the ground, there's the impulse pointing upward to prevent it sinking into the ground.
Can I make an interruption?
Right.
Is that okay to turn on the curtain?
Okay.
Any reflections?
Okay. Yeah, probably this one. Turn off one light. I think probably that would be better. Yeah. We can't complain of sunny weather. Is that better to see on the screen? Okay. Well, still I need to go on.
You know better than.
Okay.
Did you turn the light on the camera?
Yes. The light is on.
It's not as strong as the sun.
Right. Definitely nothing as strong as sound. Okay. So let me keep going. There will be one impulse direction points upward to prevent this block sinking into the ground, and also there will be another direction like this direction impulse J. This is Jn and this is J T that have some friction forces applied on this block to slow the tangential motion down. Right. So the overall impulse will be something like this. So how to do that? The first thing is I'm going to assume this one is a static friction case, which means that the JT will be strong enough to cancel the entire velocity on the tangent direction. So that means that after this collision, my new velocity u relative will be something pointing upwards. U relative nu is that direction that pointing upward because all the tangential direction component is cancelled by the friction. All right. In that case, we can write down the equation because this one equals to u relative normal. Sorry, this is a scalar. U relative normal, the new one, and multiply by the normal direction. And we know this one is the negative of epsilon multiplied by u relative normal. All right, because this is the coefficient of restitution, and I'm going to move it up a little bit. This is the coefficient of the restitution, and simply that one will reflect the original normal velocity to the new one multiplied by this n vector, and that equals to epsilon times n transpose u relative, the original one multiplied by n. Right? So we have this new velocity, and we also have the old velocity because we know that the new velocity equals to the old velocity plus some k multiplied by j. We have both of them, so we can combine those two equations together. It's basically saying that k multiplied by j equals to negative epsilon n transpose u relative n and minus u relative n. And K is a 3×3 matrix, which is also invertible. Then we can solve this J easily. And that is under the assumption that the friction is large enough to cancel all the tangential velocities of the box. So my j vector after this calculation will be something point towards this way. And it has two components. It has jn and a jt. It's so my j vector is simply my jn multiplied by the normal direction plus the jt value multiplied by the negative of tangential direction, where this one is the tangential direction. All right, and but we know that that is not happening always, because we also have the friction model. We know that the tangential, the impulse in the tangential direction cannot be larger than mu multiplied by the impulse on the normal direction. Because you cannot apply a really small impulse on the normal direction, but a really strong friction impulse. All right. So that means there's only one cone. It's a friction cone that can cause the object to act in this static friction way. But otherwise, it will slide with at maximum jt equals to mu multiplied by jn. All right. So after we know that, we can also plug our new j under this representation into the equation. And in that case, we can still, because now jt is related to jn by a factor of mu, so we can just calculate the jn without a problem. Mm-hmm. Yes?
What is the t?
Oh, sorry. So this is the t direction. The t direction is the tangential direction with respect to the original velocity. So basically, I'm saying that the impulse have two components. One is one is on the normal direction that cancels the velocity of the objects once it goes into the ground, and another direction is on the negative t direction, has a magnitude jt, which wants to slow down the motion on the tangential direction. Yes.
So the equation where you equate u relative to the new ones, in that you've
This one?
inserted a term that's n transpose u relative the one below, the equation below.
Okay. Okay.
Should it be u relative's n component or just u relative?
Let me see. All right. Now, that's true, because this is our original velocity, and our new velocity is not this one anymore. Our we can plug it into another equation over here. Let me write it down. So still, because we have the coefficients of restitution, we can write down u relative on the n component. This one equals to new one, equals to relative n component multiplied by negative epsilon. All right, this one is not a problem. Now I'm not considering the tangential motion. And this one equals to n transpose multiplied by u relative multiplied by n. Sorry, what I'm saying. It's an n transpose multiplied by the new relative velocity. And the right-hand side is epsilon multiplied by n transpose multiplied by the original relative velocity. All right, and also we know that our new velocity equals to our original velocity plus k multiplied by j. I'm going to plug j into using jn multiplied by n transpose plus jt multiplied by negative t. Sorry, and we know that jt equals to mu multiplied by jn. So it's mu multiplied by jn. And only jn is the unknown in this equation. And we can combine those two equations to have n transpose u relative plus n transpose k jn multiplied by n plus mu Jn multiplied by negative t. This one equals to negative epsilon multiplied by n transpose u relative. And everything here except Jn is unknown. And Jn is only a scalar. And then we can just solve this system to get Jn. And then, because we know that here it's already a kinetic friction model, we can apply Jt equals to mu multiplied by Jn. And then our impulse is down. All right?
But like this, it only works for collisions with the ground, right? Because like if you have two dynamic bodies interacting, then this matrix K is actually the sum of both matrices.
That's true. That's true. If because ground has infinite mass and infinite inertia. If now it's a collision between two objects, and then I assume this is the colliding point, and then the relative velocity on that point on object A will be the old relative velocity plus Ka plus Kb, this one multiplied by the impulse. All right, this is what you want to say?
Yeah.
Right, and also once we calculate the impulse applied on this A object, the impulse applied on this B object is basically negative J. So it's like Ja equals to negative Jb, or vice versa, because that's Newton's third law of motion. All right.
So what is the meaning of the Ka and Kb?
So Ka is the combination of the mass A multiply A 3×3 identity and plus inertia plus R, this Ra matrix transpose multiplied by Ia inverse multiplied by Ra star.
I think it's the inverse mass.
Right, inverse mass. Right.
So then why do you add with Kb? So is Kb, is Ka now enough?
Oh, so here's the thing, because because ground has this infinite mass, and here it's how to say that?
It's just the RB vector is different than the RA vector because it's relative to the other body. And also like you take the mass and inertia of the other body. So that's why Ka and Kb are different.
It's more like you can think that as the inverse of both its mass and inertia. As if you have an infinite one like the ground, then the Kb will simply be 0. That's the case we talked before. And if B is also movable, and it seems like okay, here's the thing. If you have a ball and you slam it into the ground, and it will get bounced back to a certain height. All right. So, but if you have another ball, also like hand in the air, and you drop it on top of another movable thing, then the impulse acted on both balls will. If those two balls are exactly the same, then the impulse of the two balls will be taken half and half of the original impulse.
Right, so you have to apply the resulting impulse on both bodies in
Right.
opposite directions.
Right. Okay. Okay, that's great. Let me keep going.